Kia ora, Year 12 and 13. This is the second excellence question from 2013's differentiation paper. I think it's probably the hardest out of the three, although if you see what to do, it's fairly straightforward. It's another optimization question, and it's about folding a sheet of copper into a trapezium. Alright, so a copper sheet of width 24 centimetres is folded, as shown, to make spouting. So here's 8 centimetres here, 8 centimetres here, and 8 centimetres here. We're asked to find the angle theta, which gives us the maximum cross-sectional area. Alright, so we're looking at whether it's better to make a trapezium that's got a very big angle here, or whether it's better to make one that's got a very shallow angle, where each of these bits is 8 centimetres long. Right, so to maximise the area, we need to think about what's the formula for the area of a trapezium. And that's half, so the average of the top and bottom sides times the height. And the height is the perpendicular height, like that. You should look at this and be thinking, okay, I've got right angle triangles popping up already. Here we are, here's one here. Pop that in. And here's the same one over there by symmetry. Right, so we've got theta on both sides. So think back to Year 10 trig, and what we've got to work out is what's this length here, and what's this one here. Okay, so firstly let's draw it out again here. I've got theta here, and I've got this little right angle triangle. I'm going to get my height first. I know that the hypotenuse must be h, and this is theta. So what's h? Well, sine theta is equal to the opposite over the hypotenuse, which in this case is h over 8. So h is equal to 8 sine theta. Looking now at the top of the trapezium, we know that, now this is actually really badly drawn, I'll do it a little bit more accurately. This bit's 8, this is 8, and this is 8. What's the bit up the top? Well, that bit there will be x, but we will be 8, sorry, but we're going to call these two end bits x. So they are coming out of the same right angle triangle. This time though, x is the length down here. Right, so if I've got x up there, it's x down here. What do I know about this? Well, this is the adjacent, and this is the hypotenuse. So I've got cos theta is equal to x over 8. X is equal to 8 cos theta. So we can say that this top bit here must equal, so that's going to be b. b must equal to 8 plus 2 lots of x. So x is 8 cos theta. So now we've nearly got enough to get going on our differentiation. Right, so we've got a equals 8, b equals 8 plus 16 cos theta, and h is equal to 8 sine theta. That gives me a nice expression for the area of a trapezium, which is going to be 1/2 times 8a plus this one, 8 plus 16 cos theta times 8 sine theta. So that equals 4 sine theta times 16 plus 16 cos theta, 64 sine theta plus 64 sine theta cos theta. Now, there's an easy way to do this, or there's a quite painful way here with the product rule. I need to find what makes this area a max. So for a maximum, we need dA by d theta to be equal to 0. You might want to pause the video here, just have a think back to trig for which easy trig identity is going to simplify that. Right, so we can rewrite our expression as a equals 64 sine theta plus 32 sine 2 theta. Now I can do that because 2 sine theta cos theta is equal to sine of 2 theta. So that's what I've used for that. Therefore, dA by d theta is equal to 64 cos theta plus 2 times 32 cos of 2 theta. 64 cos theta plus 64 cos 2 theta. And we need to set that equal to 0 and solve the equation. Right, so 64 into cos theta plus cos 2 theta equals 0. Right, time to think again about our trig identities. Cos of 2 theta is the one that has 3 extremely useful identities. We can see that we've got this angle is a cos of theta. So we're looking for the identity, hopefully, that also has cos of theta, because it's going to help me turn things into a quadratic. So cos of 2 theta is equal to 1 minus 2 cos squared theta. I'm going to rewrite this expression using this identity and then solve. Cos of theta plus 1 minus 2 cos squared theta equals 0. 2 cos squared theta minus cos theta minus 1 equals 0. So I'm just timesing through by negative 1 so that I get a positive coefficient here. If you're looking at that and thinking, oh, I can't remember, a trig was a long time ago, let's just rewrite it as 2x squared minus x minus 1 equals 0. And see that it's a very easy one to factorise. 2x times x, let's see, we want to get a minus 1 here. So it's going to be a minus 1 here and a plus 1 here. Check it back, make sure it works. 2x squared plus x minus 2x minus 1. So on the next slide, we need to pop back in cos of theta equals x and proceed to solve it. So we've got 2 cos theta minus 1 times cos theta plus 1 equals 0. Either 2 cos theta equals 1 or cos of theta equals negative 1. Think about what we want though. Theta should be between 0 and pi on 2 for our context, right? Because theta is this angle in here. So when is cos of theta equal to 1/2? Or when is cos of theta equal to negative 1? So there's no values, no solutions in our domain for this one. So we're not interested in that one. What about cos of theta equals 1/2? Well, that's nice. That gives me theta equals pi on 3, or theta equals 60 degrees. So that is the angle that is going to maximise my cross-sectional area. Notice in the question that you didn't need to prove that you found a maximum. If we did need to make that check, remember what you do, you just differentiate again and check whether your second derivative at this point is negative. Alright, thanks for watching. You're probably going to want to go through this one again pretty slowly to make sure you've got all of the steps. 2 things to trip you up in there. The first is breaking the trapezium up into the simple right angle triangles, and the second is remembering your trig identities in the right places. Thanks for watching. I'll do the last question soon.